Welcome to the second lecture of Advanced Material Chemistry Device Material part. In the last class, we learned what are the semiconductors. Then we saw some elemental and compound semiconductor materials. Elemental semiconductors are mainly silicon and germanium, and compound semiconductors are when one group element like 3,5 or 4,6, kind of when two or more materials are mixed together and they behave like semiconductor. Those are compound semiconductors. Then we saw some important crystal structures pertaining to the semiconductor materials. These are the crystal structures in which silicon or gallium arsenide crystallize, mainly diamond structure and zinc blende structure. Both structures are same. In diamond structure, we have same atom, carbon atom at all the places, while in zinc blende structure, in one FCC structure, it is gallium or one atom, on another FCC structure, which is displaced by 1/4, 1/4, 1/4 on diagonally in FCC structure. That is another element. So at one place, suppose gallium, another place arsenide. Then we also saw how a closed packed structure can form FCC or BCC, FCC or HCP lattices. There are actually tetrahedral voids. There are tetrahedral voids. So this we can understand like this. You have spheres, all three spheres, and there is a in between there is some space. And imagine that you are putting another sphere above that. So this void, which will be formed by these three plus another four, is tetrahedral void. So suppose there are two different materials. We can put another material inside this, and then have fourth one. So imagine this is a situation to understand tetrahedral void. Now you just increase the size of that red dot, which I put just before that, to the size of this sphere. So the structure in that situation, whatever structure is formed, that structure will be tetrahedral structure. And the angle between each bond in that situation is 109.5. This we saw yesterday. Then we also saw crystal planes, different crystal planes, because crystal planes are important. There are many properties of materials which are directional dependent, and therefore we got an idea about the crystal planes a little bit. Then we saw valence bond, formation of energy bands. This we try to learn in detail, because when the atoms are brought together, they form bands. Then we saw specifically for silicon how the band is formed. We will just quickly see same figure today also. Then we saw energy momentum diagram, EK diagram. So before going to that, let us see some important concepts, which some of them we learned yesterday. So the allowed energy can be found out using quantum mechanics by solving the equation, Schrodinger equation. And so now understood by all this that the motion of electron can be controlled by subjecting it to a well-controlled and well-defined periodic potential. So this property can be very well utilized in forming the devices. Now, some infinite periodic potentials can be readily provided by single crystals. In like even if it is not in a single crystal, if you pass it to an infinite periodic potential theoretically, then also you can have the same kind of features. In order to form a single crystal, we bring many atoms together, and then due to their mutual interaction, electronic energy bands are created that we saw yesterday. And bands are of two types, valence band and conduction band. The valence band is the highest range of energies in which electron can normally present at absolute zero temperature, while the conduction band is the lowest range of valence vacant electronic states. Conduction band are normally vacant at absolute zero K. The band are continuous for entire crystal. That means when an electron is in a conduction band, then it doesn't belong to a single atom. Rather, it is the property of entire crystal. So it sees entire crystal as a single unit and not as an individual atom or ion to which actually it belongs. So presence of electron in conduction band plays crucial role in the property of substances. Insulators hardly have any electron in the conduction band, and conductors have plenty of them. So it is difficult to control and regulate the flow of electrons in the substances like metals, where there are a lot of electrons are there, or if you have insulators where hardly there is an electron in the conduction band. So the most preferred kind of substances are semiconductor materials, where you can tune or where you can control the movement of the electrons. Now let us see once again the same figure. First, I will try to explain in the atom form. You have an atom, there is a nucleus, and then there are electrons. So this outer electron can either have these outer electrons can either have this energy, or can have this energy, or can have this energy, or there are some other higher energy also. So it cannot have any energy in between those. So now suppose I say that out of these 4 electrons, there is slight difference here. I have put only one, but 2 electrons are in 2s state and 2 electrons are in 3s state and 2 electrons are in 3p state. So now this electron can either stay here, or it can stay here, or it can stay here. So if it gets certain amount of energy from outside, this energy it absorbs, it can move any of those if the energy is exactly matching this value. But if the provided energy is not matching, though even if it is more than this level, this energy, and falling somewhere here, the electron will not do that. I will accept this half energy up to this, and then it will either absorb full energy, or it will not absorb any energy. So this is like the ground energy, you can say. This is the first excited energy, this is the second excited energy, and so on. But when this is silicon atom only, when many silicon atoms comes together, suppose we start from the 2 atoms, if another atom comes near to it, so this energy which was exactly here, this will ideally split into 2 levels, very closely spaced 2 levels. When you start adding more and more atoms, suppose 10 to the power 23 atoms, it's a very huge number in 1 centimeter cube. In that case, so many number of electrons, so many number of these electrons will be available in that substance, and they will be very close to each other, and the nearest neighbors will actually see some of the second, third, fourth orders. And when it is in the crystal form, then it is also inside a periodic potential. So now, so let us start from this place. This was individual atoms. Now we bring many atoms together. This goes on like this. If you start, if suppose distance between these atoms is very large, then in that case, these will behave like individual atoms. But as you start bringing them together, in that case, at this point where the atoms starting seeing or getting influenced by the other atoms wave functions, in that case, this level starts splitting. And it keeps on splitting, but still up to this point, you will see both the levels are still, this level is different, this level is different. So S and N, yeah, 3S and 3P, the levels are still different. But when they reach at this level, then both these are merged together. And now you will be having 2N plus 2N, 4N states and 4N electrons available. Obviously, they will occupy the lowest energy state. So the lower 4N states will be occupied, upper 4N state will be empty. If you go on reducing it and reach at a lattice spacing of 5.43, which is real spacing of silicon atom, in that case, the structure becomes like this. So what we see here is a conduction band and valence band is corresponding to this line here. If we can somehow compress the entire lattice to further reduce this spacing to 5.2 or somewhere here, then the conduction band will move upward, because in that case I will have here draw line here and I will draw in that case line here. So valence band will also come down, so the gap will increase. So if we try to compress the lattice very you can say exactly in the same way that all the atoms should be having 5.4 angstrom or 5.2 angstrom in place of 5.43, the structure will be like. So I hope by this you have understood how the bands are formed and how we represent them. This was one part. When the crystal is formed, there is another thing, another interesting thing is that because the crystal, inside the crystal or inside those, the atoms are also vibrating. At absolute zero, they are at the rest, but as you keep on increasing the temperature, at room temperature, they have certain thermal energy. Due to that thermal energy, the atoms are oscillating around their mean position. So here I have tried to show by this picture. This I have taken from internet. I not made it. So if you see the atom is moving around its mean position, and this is happening due to the thermal energy. There is also in this curve also you see there are various levels E0, E1, E2, E3, E4, E5. Similar to the atom which was having energy, quantized energy E1, E2, E3, these energies are also quantized energy. But the level of quantum is less here. It is in the milli-electron volt range. This is here interatomic distance. So by coming back again to this lattice structure, or you can say periodic structure of lattice, they provide, they added some constraint, and due to that, the EK curve, which for free electron would have been a parabola, now it has certain gaps. These are those gaps. This comes from the quantum mechanical solution of Schrodinger equation corresponding to this system, which says which gives this solution. And so now this parabola, which was now we consider only this small part, suppose. So for some crystals, you can have a narrow kind of parabola. For some crystals, you can have a broader parabola. And if we consider only free electron, this is the free electron EK curve. So different crystals can have different crystals have different kind of parabolas. And if you double differentiate it and take a reciprocal of that, it gives you the effective mass. Effective mass is a concept which has been introduced to explain the movement of the electron under this periodic potential. So now, based on based on the band theory, we can explain the conductivity of metals, semiconductor, and insulators. It is a qualitative explanation. So in the conductors, you can have either a partially filled conduction band, which kind of exists in case of copper, or you can have the conduction band and valence band, they are overlapping. You see, up from this point to this point, it is a valence band, and now from this point to this point, it is a conduction band. Here, it is a valence band is here and conduction. So it is, you can say it is, it is conduction band only, but it is partially filled conduction. However, if we see the insulator space, there is a large gap of about more than about 5 to 6 electron volt. Then there is absolutely no electron in conduction band, and the valence band is totally filled. When we come to the semiconductors, which are having the conductivity in between these two, the energy gap is also lying between these two. So typical energy gaps are nearly 1 electron volt to about 2.5 to 3 electron volt, where the this material even less than 1 electron volt is also there for some semiconductors. So in that case, even thermal energy can provide some electrons or promote some electrons from valence band to the conduction band. So now let us see intrinsic semiconductor. An intrinsic semiconductor is a pure semiconductor. When there is nothing is added in a semiconductor material, it is a pure silicon, suppose, or pure germanium, or pure gallium arsenide material, then it is called as the pure intrinsic semiconductor. The number of charge carriers in a intrinsic semiconductor will be it will be determined by the properties of material itself instead of amount of impurities, because there is no impurity in this. At room temperature, intrinsic semiconductor exhibits almost negligible conductivity. At absolute 0 Kelvin, they are perfectly insulated, but even at room temperature, their conductivity is low. And whatever is that conductivity, it is because of the some carriers which have been promoted due to after getting thermal energy to the conduction band. Extrinsic semiconductors are those that are the result of adding an impurity to an pure semiconductor. These are basically termed as the impure form of semiconductor. So suppose you have a pure silicon semiconductor in which you add some impurity. In that case, it will become extrinsic, and that impurity, the amount of impurity and how homogeneously it has been added to the entire crystal, it will play an important role in the properties of that substance. And this material is called, the material will be called as an extrinsic semiconductor. The process by which certain amount of impurity is provided to pure semiconductor is known as doping. This process is called as doping, where you are adding the impurity. Hence, a pure semiconductor is doped to generate an extrinsic semiconductor. So, extrinsic semiconductor is a intrinsic semiconductor added with certain amount of impurities. The extrinsic semiconductors are of two types. These are N-type and P-type. So let us know what are these N-type and P-type. Suppose we had silicon. The silicon has 4 atoms. We are considering only outermost atoms. So when we add a impurity which is having or you can say pentavalent impurity like phosphorus. So phosphorus has 5 electrons in the outermost orbit. So 4 of those electrons they make bond of silicon with the silicon, and 1 remains free. Now when you are doping by a certain process, this phosphorus, it should be throughout the crystal, it should be uniformly distributed. It's not like that the phosphorus which you have added is segregated in one part and other part is having pure form. Then it will not be a proper extrinsic semiconductor. So this I already explained. So the 5th electron, which is having a small, relatively small binding energy to host phosphorus, now it can be ionized to become conduction electron at the moderate temperature. So now why we call it a donor? Because this effectively we can say that this electron has been donated by phosphorus to the lattice or to the material. So the phosphorus atom is then called as a donor, and silicon become N-type, because N-type means negative charge carrier it is having. So it is having, now it is having extra electrons, so it can be that's why it is called as the N-type. So now if we will see in the band formation, so in the case of intrinsic, suppose we see it was conduction band and valence band, and there was nothing in between that. These all were not allowed. If you add a donor material like phosphorus, then in that case, the energy levels are created very near to the conduction band here. Since they are very small amount of impurities which are added, therefore there will be, it will not be a continuous kind of line, but there will be small localized lines. So now by adding phosphorus or adding N-type some pentavalent material, you are adding certain levels here, and this is the typical band structure of an N-type semiconductor. N-type semiconductor is obviously it is an extrinsic semiconductor. Similarly, when boron atom with 3 valence electrons substitute for silicon atom, an additional electron is accepted to form 4 covalent bonds around the boron. So let us, if we see the same situation where in place of phosphorus, if we put a boron, so there are 4 electrons, silicon, all 4 electrons, and then boron will be having less. So in that case, there will be 1 electron missing. It can accept 1 electron. Suppose 1 electron is available somewhere here. This can accept the electron, and therefore such kind of absence of hole, absence of electron is called as hole. So hole is nothing, but it is an absence of electron. We can understand the movement of electron, but it is very difficult to realize the movement of hole we always say that holes are moving, but holes are actually nothing. It is opposite of electron, moving electrons only. So in this animation, you see there is a hole. So here it was a hole. Now electron has come from this place to this place. So hole has moved from this place to this place, this place to this place, and to this place. So if you see, actually the electron is moving, but as a consequence of that, the hole is appear to be moving from one place to the another place. So a vacancy is moving from one place to the another place. So this is this kind of semiconductors where holes are used, where holes are, can say, majority of the type of carriers are called as p-type material. The mobility of holes is relatively less than that of the electrons. So these n-type and p-type materials, these are created by adding different dopants. So what are different dopants? I explained two different dopants, that was boron and phosphorus. There are some other dopants also which can be used, in particular in the case of silicon, which has a band gap of 1.12 electron volt. So these are the ionization energies. Ionization energy is the same energy by which you can lift an electron from certain levels to the conduction band here in the semiconductor. So you have carbon, where it's nearly 0.25, platinum 0.25. These are the different materials. Gold, if you dope the same with the gold, they will create a level which is very close to the mid of the Fermi level, mid of the band, and very close to the Fermi level. If you dope with the antimony, which is a very close energy level now, at 0.039, and so even at room temperature, all these will be ionized, because room temperature is room temperature energy, thermal energy is 0.025 electron volt. So these are also very close energy levels, and so these are different impurities. Boron with this level, aluminum, gallium, indium, palladium. These are different dopants. But most of the material, most of the dopants in like most of the in devices, boron and phosphorus are most commonly used. Now let us also understand what is non-degenerate and degenerate semiconductors. So if the electron or hole concentration is much lower than the effective density of the states. Effective density of states, what is the density of states? Is total number of allowed energy states per unit energy per unit volume is the density of states. So the hole concentration or electron concentration, let us say we are considering suppose n-type material, is less than the effective density of states. Means the states are more. It can accommodate more and more electrons, but available electrons are very less. So in that case, it is called as the non-degenerate semiconductor. The Fermi level is at least should be at least 3 kT above the EV value, or 3 kT below the EC value. EC value is the energy corresponding to the bottom of the conduction band, and EV value is the energy corresponding to the top of the valence band. Now this was not the non-degenerate. Non-degenerate means when the number of electrons, available electrons, are less, very less as compared to the total number of energy levels which are available. However, when the doping concentration becomes very high, you make a very high doping. In that case, when it becomes to equal or larger than the corresponding effective density of states, the semiconductor is referred to as the degenerate semiconductor. For a very heavily doped n-type or p-type semiconductor, EF becomes, it will be above EC in case of n-type semiconductors, and below EV in type of p-type semiconductor. Effectively, it behaves like a very good conductor, or some say metal kind of behavior when you have a very high doping. Now, if you go on increasing the concentration, the band gap also changes. So if the doping concentration is increased to this much higher, 3 to 10 to the power 19 centimeter cube, then the band gap, which was 1.12, it becomes 0.12 electron volt. This is 10% of the shell band gap. Now, we have seen different kind of semiconductor materials. Now, how the carriers moves inside a semiconductor. Carriers means it can be electron or it can be holes. Since we understand easily the electrons, mostly I will say electron, but it is equally applicable to holes also. So various transport processes are taking place in a semiconductor. These are drift, diffusion. Electron can move by diffusion, electron can move by drift, and you can generate electron. You can have generation also, recombination process also, then thermionic emissions of electron, tunneling of electrons from one you can say volume to another volume, or one place to another place, and space charge effect, impact ionization. These are all transport processes which affects the movement of carriers. It is equally applicable to both electrons and holes in the same way. Only thing is hole moves opposite in opposite direction. Now let us see what is drift current. The conduction electron in the semiconductor, the conduction band, they behave like free particles. Why they behave free particles? Because if they are very less and conduction band is free, in that case, whatever voltage you apply, the corresponding raise in the energy of electron is also available in the same band. That energy level is also available, so it can easily accept. So in that case, it easily, the electron which is subjected to any potential can accept any potential value and increase its energy. So if it can take all energies, it can very well accept, behave like a free particle, because there is no restriction. Suppose it is in a band, suppose it is in a valence band, and you apply certain amount of voltage, and the energy is just above the valence band in the just above the valence band in the forbidden region, it will not accept that energy. Now, before taking that, when electron is moving, when electron is behaving like a free particle, it can have random motions. It can move in one direction, then after certain, it will move into another direction because of the thermal energy it is already having. So it will be keep on moving, but over a period of time, if you average this, average out this motion, and it becomes total average displacement will become 0. So like one time it has moved in right direction, sometimes it will move to the left, sometimes to the top, sometimes to the bottom, but over a large period of time, if you will see, the position will remain same. But when you apply small amount of electric field, in that case, what happens? Each electron will experience a force because of this electric field, and it will be accelerated along the field. So now again it will move in this direction, but it will also collide with some other metal, some other atom. Again stop, then again get accelerated due to this E. So in the process, if you see on a long time, because of the effect of this electric field, it will have a net displacement. This kind of motion is called as the drift. So an additional velocity component will be superimposed upon the thermal motion of the electrons. This component is called as the drift velocity. Due to this drift, there is a net displacement of electrons in the direction opposite to the applied field. At low fields, the drift velocity is proportional to the electric field. At low field, if you increase the field to very high level, then you have some other components also coming into picture where this electrons start ionizing other atoms. But at low fields or reasonable fields, the drift velocity is directly proportional to the electric field. More the electric field, you have higher the drift velocity. And this proportionality constant, you have a velocity, it is proportional to the E, and then if you remove the proportionality constant, this is called as the mobility. So mobility will be of two, we can say, for electron also, for holes also. So electron mobility is represented by mu n, and hole mobility is represented by mu p. So the total drift current now will be, if there are electrons and holes both are there, so the total drift current will be J is equal to the drift current due to electrons plus the drift current due to the holes, and so charge En multiplied by mu n, and the charge multiplied by number of N is here, number of carriers. So here and multiplied by E. So this will be the total drift current density. This was the drift current. Now let us see the diffusion current. Why diffusion happens? Because from our basics, diffusion happens when there is a concentration gradient. So another current component exists if there is a special variation of the carrier concentration. Means carrier concentration is higher at one place and lower at another place. So if a semiconductor is having such kind of you can say configuration where it sees that at one place you have more number of carriers, and another place there are less number of carriers. So these carriers will move from one place to another place, and since the carriers are moving, so the current is also moving. So the carrier tends to move from a region of high concentration to a region of low concentration. This current component is called as the diffusion current, and this can be given as by, this is suppose diffusion current density, this is dN by dx is a gradient of concentration, and dN is diffusion coefficient and Q is the charge. We have drift and diffusion in their we can say very common transport process. In addition to this, we have other transport processes also. The number one is thermoionic emission. So it happens when carriers in the surface region or the surface of your substance, they gain enough energy and they emit it out of the surface. So they emitted out means they have gone into, as per the energy level diagram is concerned, they have gone into vacuum. So thermoionic emission is usually happens. This happens when the thermal energy is very high. Usually. Then tunneling process. This process is based on the quantum tunneling phenomena that results in the transport of electrons across a potential barrier, even if the electron energy is smaller than the barrier height. Tunneling process happens. It's a so suppose you have a very high barrier of suppose few keV, and your electron is having only few eV energy. So ideally, that electron can never cross that barrier because it requires more energy. It's like in a physical expression, if I try to say that you are seeing a wall and you are the energy required to break the wall is very high, you cannot break it. Your energy is very less, but you are still hitting. You are still hitting, and then so it's the same way electron is hitting a barrier. That barrier energy is very high, but quantum mechanics says that every hit has certain amount of probability. So tunneling, in the tunneling process, what happens? The electron can just move without breaking the wall. Though energy is high, it can move to another direction. That is called tunneling. In the same example, like I was saying, you are hitting a wall. So in the quantum mechanically, this tunneling process I can explain this way. You are hitting the wall, you have hit millions of times, and in one attempt, you found yourself on the other side of the wall. That is the tunneling process. Though it looks difficult to imagine, but it happens. This is the tunneling. Next is space charge limited current, where the injected carriers are not compensated by the ionized impurities. So when you have injected carrier, those carriers, and they have not recombined, in that case, that there will be a space charge generated inside the semiconductor, and because of that also there will be a movement of carriers. There are other process of like impact ionization. Impact ionization is when the field, suppose you are having an electron and you have applied a field. So this will, the electron will get attracted due to this field. It will experience a force, and then it will start moving. So when this field exceeds a certain value, the carriers gain enough kinetic energy to generate electron hole pair through a Coulombic method. Suppose you have gained, suppose you have a material in which the ionization energy is about 4 electron volt or 5 electron volt for any atom. And the electron which is accelerated due to this field have gained much more energy than this 4 electron volt, or if suppose there is 100 electron volt. In that case, what it can do, this electron, it is moving with very high speed and strike with that electron, and it can eject out that electron from the core. So what it has done, now it has created another electron which will also be there in the which will also be experiencing the same electric field which it the electron, the original electron was experiencing. So now you have two electrons moving in the same under the same electric field, and in this process, this electron which has come out from the atom has also created another hole, or this ion is left. So this effect is important in PN junctions. When we see Zener diodes, they are based on this principle. The high field, this high field accelerated these new electron hole pair, which collides with the lattice to create more electron hole pairs. So as I said, suppose initially there was one electron. Now this electron has struck with a electron which was there inside an atom, and it has removed that electron. Now there are two electrons. They will also experience, both of them will experience the same field within short period of time. That another electron will generate the same energy, we will get the same energy, and it will be capable to create more and more electron hole pair by striking the number. So within a short period of time, you have a lot of electron hole pairs inside that material. And so if you are measuring the current, you will get a very, very high current. So as this process called impact ionization or the avalanche process continues, the PN junction breaks down and conducts a large amount of current. Let us understand now with all this information in our mind, what are P-type or N-type semiconductors in a slightly, you can say, different way, or PN type, PN junction kind of way. So first, some things we understand. This is valence band, which we have already seen, and there are initially there was nothing. All the electrons were there in the valence band, and this is conduction band. There was no electron in the conduction. So what are different these values? This is EV, as I already explained. This is the top of the valence band. EC is the bottom of the conduction band, and EFI is the Fermi energy at the intrinsic for the semiconductor, intrinsic semiconductor. What is Fermi energy? Fermi energy is the probability of Fermi energy, you can say, is that energy where probability of finding out an electron is exactly half. So now you see below this energy, all the levels are totally occupied, and above this, all the levels are totally empty. So exactly at the center of this gap, the probability will be exact half. Suppose these two are, there is no gap. In that case, at the junction value, below that, all the electrons are occupied, all the energy levels are occupied by the electrons, and above which all the electrons are empty, will be considered the EFI. So in case of metal, the highest field level will be the Fermi energy. So now what is this is phi. Phi is the work function. So actually it should not, let us assume that the top of the conduction band is actually vacuum. So this is the work function. Work function is amount, this energy is amount of energy to remove an electron to vacuum. So here work function is, in case of intrinsic semiconductor, it is a energy difference between the Fermi level and the vacuum level. Suppose this is vacuum level there, and this is electron affinity. Chi is electron affinity. What is the electron affinity? Is the energy difference between EC and the vacuum level. In intrinsic semiconductor, N, the number of holes, is equal to number of electrons. Because suppose they are initially all the levels were filled, you have provided certain thermal energy. In that case, suppose few electrons have reached from this level to this level, so you will have same number of holes in the valence band and same number of electrons in the conduction band. So the law is that in the case of Ni square is equal to N into P. Now, if we see here, in case of N type of material, the Fermi level is slightly so this is suppose this is conduction band. This Fermi level in N type material is close to the conduction band, and on the other hand, Fermi level in the P type of materials where holes are used is very close to the valence band. This you should be knowing very clearly, because when we will make junction devices, then this role of this Fermi level and its alignment becomes important. So when you fabricate PN junction or first technologies in the IC fabrication technology, which is used is the planar technology. In the planar process, the planar technology utilize oxidation, lithography, ion implantation, and metallization steps. In addition to some cleaning and other things, these are the main steps in a planar technology by which usually PN junctions are formed. PN junctions are mostly formed. So most important characteristics of PN junction is that they rectify, that is, they allow current to flow easily only in one direction. Why? When you will join these two, immediately the Fermi level has to align. Once the Fermi level align, what will happen? This will go up, this will come down, and in that case, what will happen? A voltage will be developed. That voltage will oppose the movement of the electron in one direction, and they will promote the movement of electron in another direction. It is opposite to holes. Two regions of P and N type semiconductor materials that are uniformly doped and physically separated before the junction is formed by this process. The Fermi level is near the valence band as in P type material and near the conduction band as in the N type material, as I said here. While P type materials contains a large concentration of holes and only few electrons, that is minority charge carriers, the opposite is true for N type materials, where large concentration of electrons are there and very few holes are there. So now when we join them, suppose let us just see this animation. So we have P-type materials, we have N-type material. When you add them, so the electrons will move from this because and then they will try to neutralize these holes. So over a certain period of time, what you will observe is that a space is created where actually there is no free carriers. So this, when these are joined, the large carrier concentration gradient there, because here is lot of electrons are there, and there is actually it's absence of electrons, so you will see a very large concentration gradient, and there obviously because of this concentration gradient, carriers has to move from one side to another side. So holes diffuse from P side to N side. It is diffusion actually, and electrons from N side to P side. Actually, it is electrons only which are moving from one side to N side to P side. As hole continues to leave P side, some of the negative acceptor ions near the junction are left uncompensated, and acceptors are fixed in the semiconductor lattice. So as holes are moving, so you will see after some time a net positive voltage will be generated. So a negative space charge formed near the P side of the junction and a positive space charge formed near the N side. Now, due to this, there will be an effective voltage. This space charge region creates an electric field that is directed from the positive charge towards the negative charge. Electric fields always from positive to negative. So this is here shown here in this. So you have now, because of so this is actually, you see this gap from, if you set this minus this, so there will be effectively a potential is developed. The electric field in this direction opposite to the diffusion current for each type of charge carrier. So the electron diffusion current also flows from the left to right, where the electron drift current flows from the opposite, in the opposite direction. So now you will be having two currents. One is the diffusion current, which was flowing initially due to the carrier concentration gradient. Now, because of this flow of the electrons from one side to another side, a electric field is generated because you had some positive charge in one side and negative charge in the other side. Now this is opposite to the original movement. This will oppose the original movement, and so because of that, it will start pulling the electron back. Suppose electron has moved from this side to this side, the effective electric field which has been created is to try to pull back those electrons here. So it is not like that all the electrons will go and combine here. After a certain time, an equilibrium will be established. So at thermal equilibrium, that is at steady state conditions, at a given temperature, with no external excitation, the individual electrons and hole currents flowing across the junctions are identically zero. So neither electron will move from one side to another side, nor hole will move from one side, and then this total current will be zero. Thus, for each type of carrier, the diff current due to electric field must exactly cancel the diffusion current due to the concentration gradient. So in this was like how a PN junction, and then how a PN junction, when it is formed, you get this kind of behavior where electrons move from one side to another side, and then you have a electric field or a built-in potential developed. This is called as a built-in potential. This built-in potential, it depends on the Fermi level difference between N type and P type, and this built-in potential is material specific. Normally, if you have you are not changing the component of your material, the built-in potential will be constant. You understand this process because solar cell also work on this principle, junction diode also, where we utilize this these properties. Now, how the carriers can be generated or they can be recombined. That, as I already explained, in thermal equilibrium, the relationship number of charge carriers, N-type carriers, and number of P-type carriers. If you multiply them, this becomes equal to the square of intrinsic carrier density. This remains valid all the time, where P and N is the density of electrons and holes, and I is the intrinsic carrier density. So remember, whenever you want to find out the carrier concentration after doping, after making doping with the certain concentration, in some numerical questions it comes like that. You have been given a problem that a material has been doped with so many concentration. Then find out the concentration of the carrier concentration of other, where you have to, in all such problems, you have to apply this equation, which is a valid equation all the time. So if excess carrier are introduced to a semiconductor, so that temporarily P and I, P multiplied by N becomes more than Ni square, we have this equation. This equation is called as the non-equilibrium situation. The process of introducing excess carrier is called as the carrier injection. So most semiconductor devices operate by creation of charge carrier in excess of the thermal equilibrium values. Whatever was available in the thermal equilibrium, the excess charges are created more than. So we can introduce excess carriers by optical excitation, where you can excite the junction with a photon, and the energy of the photon should be higher than the that of the band gap. In that case, the electron will be the energy will be absorbed by that electron, and it will go to the conduction. So excess carriers by optical excitation, or then you can also do it by forward biasing a PN junction. Forward biasing means you are inserting current by applying a voltage in a forward bias. So whenever the thermal equilibrium condition is disturbed, that is, as I already said, P into N is not equal to Ni square, then there are certain processes which exist to restore the system to the equilibrium state, which should be P into N into is equal to Ni square. So in the case of injection of excess carriers, the mechanism that restore equilibrium is the recombination of injected minority carriers with the majority carrier. Suppose you have you are injecting carriers, they will recombine with the majority carriers there. And depending upon the nature of recombination process, the energy released from the recombination process can be emitted as a photon, or it can be dissipated as a heat to the lattice. If the recombination is taking place and the energy release is in very, you can say, milli electron volt range, in that case, it will be a phonon emission or heat emission. And if energy is energy is very high in few electron volts, in that case, it will be in the form of a photon. When a photon is emitted, the process is called as radiative recombination. Otherwise, it is called as non-radiative recombination. So when you observe a photon out of this recombination, then this process is radiative. And in case of if you are getting only heat, in that case the process is non-radiative. So here, if you just try to explain, this is thermal generation. This is the thermal recombination. Thermal generation means at every temperature, certain due to Maxwell-Boltzmann distribution, certain even the temperature, room temperature energy is very low, but still a certain fraction of the electrons will have sufficient energy to which is equal to more than this. So all those electrons will move from the valence band to the conduction band, and now they will keep on moving from valence band to conduction band, and similarly they will keep on recombining also. So the thermal equilibrium will remain that some electrons will be there, but more electrons will grow from here and the more electrons will come back. So this is thermal generation and recombination. If we try to illuminate, you have illuminating with H nu, electron will move from this place to this place, and extra carrier is generated. It can also come back here and recombine and emit the same amount of energy. So recombination phenomena can be classified as direct and indirect processes. That I yesterday when we explained that in a direct process, the transition takes place from the bottom of the valence band to the top of the conduction band, and there is no momentum changes involved. So direct recombination, also called band-to-band recombination, usually dominates in the direct band gap materials such as gallium arsenide. And what are direct band gap materials? Are these materials where actually the bottom of the conduction band is having the same value of momentum, which is at the top of the valence band. So now holes, the electrons has moved from this place to this place, leaving 3 holes. 3 electrons have moved from this place to this place. However, if you want to understand the indirect band gap materials, how the transition takes place. So this is they have to absorb. They have to absorb. This is actually they have to absorb this much radiation, and corresponding to this much energy, a photon has to be absorbed. So they have to actually absorb the band gap energy plus the energy required equivalent to this movement, that is thermal energy. So both photons and phonons are involved in this process. So as I said, indirect recombination via band gap recombination center dominates in indirect band gap semiconductors, which is there are two most important semiconductors which are gallium arsenide and silicon. Silicon is an indirect band gap material and gallium arsenide is a direct band gap material. So for an indirect band gap semiconductor, a direct recombination process is very unlikely because the electrons at the bottom of the conduction band have non-zero momentum with respect to the holes at the top of the valence band. So a direct transition that conserves both energy and momentum is not possible without a simultaneous lattice interaction. So lattice has to interact. When lattice interacts, it interacts with the lattice vibrations or phonons. Therefore, the dominant recombination process in such semiconductors is a indirect transition via localized energy states in the forbidden energy group. So these states act as a stepping stone between the conduction band and the valence band. Now, how to measure the carrier lifetime? What is the carrier lifetime? Carrier lifetime is once you have excited an electron from the valence band to the conduction band. In that case, after some time, this electron will actually fall back into the valence band. So the time which it spends here before it recombines is called as the carrier lifetime. Carrier lifetime, very simple, as the name itself says, lifetime of the carrier. So an electron which was ejected or which was lifted from the valence band to the conduction band, how much life it has before it recombines back. I'm not talking about now it has been drifted away by electric field. That is a different thing. So how to measure that lifetime? It is very important property in semiconductor physics to measure the carrier lifetime, and it plays very vital role in different kind of devices, semiconductor devices. So how to measure it? So you have that semiconductor material and you keep on illuminating it with photons. What will happen? The amount of, and then you apply a voltage and try to measure the current. So when there was no illumination, so because there are no carriers in a conduction band, so there will not be any current. Let us assume a perfectly theoretical process where the semiconductor where the semiconductor material does not have any electrons in the conduction band, and now I apply voltage across this semiconductor material. Since there is no electron, so there will not be any current. So if I now measure here, there will not be any current in the beginning. But as soon as I start illuminating it, now there will be electrons in the conduction band. So as there are number of electrons, now we have applied the potential also, voltage is already applied. So those electrons will conduct and a current will start to flow. So this current we can keep on measuring. Now initially when you have started illuminating, so immediately all electrons will not reach there in the conduction band. So you will have a certain rise time, but after certain time it will become in equilibrium. If the illumination intensity is constant, in that case the light will also light will remain constant. In that case the current will also become constant. So you measure this current, and then after that you suddenly stop the illumination. You just switch off the light, which is the source of this light. Then what will happen? This carrier will start to recombine. So as the carrier starts recombining, what will happen? The current will start to fall, because now slowly less and less number of carriers are available in the conduction band. So the current will follow this path. So by this path, recording this path, you can easily calculate the time period, lifetime of the carriers in a conduction band. So now let us come to the context, which is also very important point, very important thing in the making of the semiconductor devices. So there are two type of metal semiconductor contacts, the rectifying and non-rectifying. The non-rectifying contacts are called as the ohmic type of contacts. The first practical semiconductor device was a metal semiconductor contact, where a metallic whisker was just pressed against a semiconductor, and with that a point contact rectifier was made. It was you can say passing current only in one direction. It was proposed that the rectifying behavior could arise from the potential barrier as a result of the stable space charge in the semiconductor. Initially, it was both. The model arising from this concept is known as the Schottky Bearing. So what is Schottky barrier? It's you have a metal contact. Metal is made to contact with the semiconductor. So metal semiconductor contacts can also be non-rectifying, where the contacts has negligible resistance for both polarities. There are special methods by which the ohmic contacts are also prepared. This type of contacts are called as the ohmic contacts. They are separate methods actually to make. Always remember that when you add a metal to a semiconductor, there will always be a Schottky barrier, and because of that barrier, there will be you can say the flow of current will be opposed in one direction because of this barrier. Some of the carriers will be opposed. Some carriers will be you can say promoted to transfer, and some will be opposed. So all semiconductor devices as well as integrated circuits need ohmic contact so that connections to other devices in an electronic system. Now, when you are making a device, and as I just now said that if you make a metal contact, in that case, there will be a rectifying behavior. Means current will not pass in both the directions. But in normal devices, whatever devices we are using, we want to have there should be at least in context part, the current should be flowing in both the directions. So for that, one has to make connections. They are following ohmic contacts. Ohmic contact means direction independent. So let us consider the one-dimensional structure of the metal semiconductor contact. Now, so how this is suppose a semiconducter and a metal is fused over this semiconductor on one side, and then we can have a contact here, and then you apply voltage. So if we see the band diagram, now metal, as we saw, as we see earlier, the metal, the Fermi level is the highest occupied level. It can be either it can be having an overlapping valence band and conduction band, or there may be in half field. In both the cases, since the number of electrons are occupied below that level, all the electrons are occupied, all the states are occupied by electrons, and above that level, all the states are empty. Therefore, the level below which all the electrons are there. The electrons are means it is totally filled. So this is called as the Fermi level. So now the Fermi level in metal and the difference between Fermi level and vacuum level is the work function. So for a metal, it is the work function. Now in this side, we see the semiconductor material. semiconductor material. This is the Fermi level and difference. This is the work function of the semiconductor material. This is the electron affinity. That is the top of the bottom of the conduction band. And so this difference between these two, that is actually a potential which is opposing the movement of electron, will be the difference between this work function minus the electron affinity. So metal work function is generally different from the semiconductor metal work function. Here we see, here it is slightly different, here it is different. In very rare cases they match. So at the electron affinity, this I have already explained to you. So now when you fuse them together, what will happen? When the metal makes intimate contact with the semiconductor, the Fermi levels of two materials must be equal in the thermal equilibrium. This is the first condition. So whenever you are adding two materials under thermal equilibrium, the Fermi level should be aligning. This is must. So always whenever you are trying to draw a diagram, you are having two individual diagram of two semiconductor or two heterojunctions also, or any kind of thing. First thing is that on thermal equilibrium, the Fermi level has to align. In addition to that, the vacuum level must also be continuous. So this is the vacuum level. So the vacuum level should be continuous. So these two requirements determine a unique energy band diagram for the ideal metal semiconductor contact. So now in our case, our case of metal semiconductor case, the barrier height Q5Bn is simply the difference between the metal work function and the semiconductor electron affinity, as I explained in the earlier slide. And therefore, the VBI is the built-in potential. So it will become equal to the difference between the these values. So VBI will be the potential that is actually potential difference that is seen by the electrons in conduction band, and they are trying to move into the metallic side. So so in one side they will experience the movement of electrons. In one side they will experience a potential, therefore they will not move in the direction. So that explains how the rectifying behavior of a diode is the rectifying behavior of the diode is due to this potential difference, this built-in potential which has been generated. Now, if you have like different different metals which you can use with the different semiconductors to get different height, different barrier height. So here, like for silicon, we will because mostly we are seeing silicon only. So suppose we have N-type silicon. In that case, this material like magnesium, it will see about 0.4 electron volt. Aluminium will see about 0.65 electron volt. So this is the barrier height, means you require at least this much voltage. This is the barrier height, at least this much voltage, so that current can start flowing. Before you apply this voltage, there will not be any current inside this junction. So depending upon the requirement of your device or requirement of whatever you plan to make, you can select the forward bias voltage by selecting different materials. You can select these, you can do experiment on your own things also. So now next comes, we have seen PN junction also, we have seen recombination, all those things. Now we will come to the heterojunction. A heterojunction is an interface between two layers or regions of dissimilar semiconductor. What is heterojunction? Is gap is different. So it is possible to engineer the electronic energy band in many solid state devices applications. For example, So all the devices that can be constructed from the using the semiconductor materials. And these devices, any device there are certain building blocks. Using those building blocks, devices are degraded. So all the semiconductor devices, there are certain number of device building blocks. I will explain one by one. Number one, the first building block is the metal semiconductor interface or metal semiconductor contact. So this is an intimate contact between a metal and semiconductor. This interface can be used to rectifying contact also, and in other at some other places also. The second building block is a PN junction, in which N-type semiconductor and P-type semiconductors are fused together. And this is also a key building block for the most semiconducting devices. Then the third building block is a heterojunction, where the interface is found between two dissimilar semiconductors. For example, gallium arsenide and aluminum arsenide can be joined together, and they are having different band gaps, and so this will create a heterojunction. So this is also a building block. So first building block, metal semiconductor. Second building block, when you have P-type and N-type, you are joining together. Then one semiconductor to another semiconductor, heterojunction. That is the third building block. And the another most important, all are actually important. Another important building block is the metal oxide semiconductor structure. So in which you have a semiconductor and a metal, and in between those two, a very thin layer of oxide is added. So you have MOS structure. This structure can be considered as a combination of metal oxide interface and an oxide semiconductor interface. By using the MOS structure as the gate and two PN structures at the source and drain, we can form MOSFET device, and we can form number of different devices by using these kind of these four important building blocks. So if suppose someone asks you what are the important devices building blocks for semiconductor devices, making semiconductor devices, these are the four. You will find only these two other than the connections. Somewhere or other, different combinations, series parallel combination, or different kind of permutation combination of these four building blocks. So these are invention of major semiconductor devices, which I have put one by one, like metal semiconductor contact, then light emitting diode and bipolar transistors were in 1947. After that, there was a you can say rapid growth. This was a path-breaking invention. Then PN junction, thyristors, then solar cells. Based on those heterojunction bipolar transistors, tunnel diode, MOSFET, laser, heterostructure lasers, MESFETs, non-volatile semiconductor memories, charge coupled devices, region internal devices. And now, like in 2004, the MOSFET, the channel length is as low as 5 nanometers. And these are key semiconductor technologies. The Chauhan's crystal growth we will see, because that is part of our course, how to grow single crystals, Bridgman crystal growth, and then compounds, hard forth, diffusion, lithographic, photorays. Using photorays, lithographic techniques are also very important. That is also given a lot of, you can say, help in developing the speed and masking, epitaxial CVD growth, ion implantation, hybrid integrated circuits, MOCVD, molecular beam epitaxy, and microprocessor, of course, with the mention of microprocessor. Now we see so many computers with a very every 6 months the speed is increased with a great, and then ALD. So with this, I think some of these slides I must tell I have taken from different acknowledgement from different sources and internet, and I acknowledge that. I think with that, I should stop here, and I'm ready to answer if you have any questions. Well, if there are no questions, then we stop here and see you on Friday. Bye.